So yeah, my name is Iuri Rocha. I come from civil engineering faculty, and I do a lot of research on materials, like how to model material behavior. We use materials for a lot of stuff, and sometimes it's very difficult to understand how they behave. So I use like computational modeling techniques for that, and also a lot of machine learning now. So that's what I will present. So this presentation has work from a bunch of people, but mainly Marina, Joop, and Nora, who will work on their PhDs with me. And there will be some graphs at the end, I promise, but it will take a while to get there. But hopefully you will see the thread work. So, like I said, our motivation is to model high performance and complex materials, right? So we rely on high performance materials for a lot of stuff. You can see some applications here. Wind turbine blades is a big one. Every few weeks, one of these blades just decides to drop from the turbine for no good reason, and they are made of very high performance, lightweight materials that are not fully understood. So it's kind of a concern to understand how this happens. Airplanes are made of high performance materials, of course, they need to be very light. Um, Also, other applications like prosthetics. There is a lot that can be done with high performance materials, and people are investing a lot of time and money in that. And there's a bunch of cool new materials coming up, which are first very complex. So this is an example from my own work. This is a fiber reinforced composite material. So if you get a piece of this material and put it under the microscope, you see that it's made out of like these small fibers and some resin around them. Fibers are arranged in this like non-trivial way, right? That affects their behavior. So this comes from another group. It's a liquid crystal polymer that you can like very finely with 3D printing align it in specific directions for it to have very specific behavior. So very fancy stuff. This is quite cool as well. It's like living materials. So this is a material made out of fungus. So we 3D print these filaments and they are inoculated with fungi, and fungus grows between the filaments and it turns into a material that can carry some load. Very interesting stuff, but very complicated, right? So the goal is to better understand these new materials that are coming up. And usually the way this was usually done was to, okay, let's manufacture something and then test it experimentally and then change some stuff and test it again. And this approach is very expensive and time consuming. So just coming up with these new materials and new structures purely with experiments is a no-go. So that's why we work with models. So we work with something that is called virtual testing. We get pieces of material and we test it, but virtually with models. And this can be done in a few different fronts. One of them is multi-scale modeling. So that's what you see here on the screen. Like if you take a piece of material and look at the microscope, you see that it has multiple scales of observation. And the material behavior depends on both of these scales. The goal is to use computer models to try to understand what's happening. I'll show a more specific example of this. And the more we know about these materials, the more efficient we can make the designs. So that's the idea. There's also uncertainty quantification. So material properties are uncertain, right? Are stochastic in nature. And it is very important to be able to compute what is the probability that an airplane fails, right? Or a wind turbine fails. And this can be done with computer models as well. And the other front is design optimization. This is kind of a new direction. And it asks like, would it be possible to design materials at very small scales for very big like applications, so like in a very specific way. So like material for the wing of an airplane to have a very specific microscopic structure. This can also be done with computer models. These three fronts is what we try to focus on. And I'll show an example now. for the first application, so multi-scale modeling. So I mentioned wind turbine blades before. So this is a maybe not very good drawing of a wind turbine blade, but if you cut a wind turbine blade and you look at the material inside, you'll see that it's made out of this, what we call composite material, that we stack in layers. And if we look closely, we see, like again, like I said, these fibers, right, embedded into this material. So there's a clear multi-scale nature material. And something I did in the past was try to understand what happened when we got this material and we immersed it in hot water for some time. Because the hypothesis is that wind turbine blades are exposed to environments, to extreme environments during their lifetime, and it's important to know what happens when like wind turbine blades take up water with time, right? So I put them in a bucket of hot water, and they came out looking a bit ugly. So I was like, okay, something happened already there. But then I put them in a testing machine. So we have these, I don't know if this is the first time you guys see this, but we have these test frames where we put pieces of materials. This thing comes down and the material gets broken, and we record how much force we need to in order to break it. And then we see that after the specimens come out of the bucket of hot water, they fail with like half of the load. So like they lost half of their like capacity to carry load, which is quite a lot, right? Quite a lot of loss. So we wanted to try to understand this. So what I did was I set up a finite element model for this material. So now, okay, let's try to use physics to model this. So I modeled like how water diffused into the specimen. So I modeled just like, you can imagine the specimen coming out of the screen here. It's just a cross section of the specimen. Water is coming out on all sides. And because water makes the material swell, right? It makes it expand. If you look at the picture on the right, we also model the mechanical behavior of the specimen, and we see that it expands, right? Like a sponge. So we model these two physics at the same time, fusion and stress equilibrium, which is very cool, but it still doesn't explain why the material loses half of its capacity to carry load. And if we take a piece of this material and we put it in a microscope, before and after we put it in the bucket, we see that like after contact with water, the material is full of cracks. So what you can see here is that some of these fibers detach from the other parts of the material. So we were like, okay, the whatever degradation happens at this small scale, but we are modeling something at a higher scale, so there's a disconnect. Right, so what I did was to try to model what happens when the material absorbed water at this very small scale. So I came up with this different finite element model, but now at this scale. And you can see it swelling, right, as it absorbs water. And then I use very complicated like material models in here to model how the material breaks when water comes in. That's why you see, like if you look here, some fibers are detaching from the resin. And also here you can imagine the fibers coming out of the screen that way. So very detailed model at this scale. This takes like about an hour to run. But again, we were interested in the behavior of the whole specimen, right? Not just a very tiny piece of it. So that's why we had to do multi-scale modeling. So we wanted to do modeling at this scale and at this scale at the same time. And we did do that by like at every finite element, at every triangle here at this scale, we embed another finite element model at the lower scale. So to run this model, we had to run a bunch of these. So this was very expensive, right? So in this case, this model would take a couple of months to run. So that's quite expensive. And that's actually for all the three applications I showed, multi-scale modeling, uncertainty quantification, and design optimization, that's the common thread is that it takes a long time to run. So these models can take months to run. And if we want to design something new and we need to do some simulations and we see that it would take a few years for them to run, that's not feasible, right? So
This is not even probabilistic, just one run.
this is just one run.
Yeah.
Yeah. So if one run here takes a month or two, if you then assume, okay, let's try to do this as well, like the material properties here are uncertain, then I need to do this 10,000 times. So then it takes a few hundred years to run. So that's infeasible, right? Okay, so this is where I apply machine learning. And to keep it simple, let's just focus on multi-scale modeling for now. So what I showed is a technique called FE squared, so finite element squared. And the squared is there because we use finite elements at two scales at the same time. So we put finite element models inside finite element models. Very powerful, but it's very heavy to run. So what a lot of people do is use surrogate modeling. So that's where machine learning comes in. So what a lot of people do is they run this microscopic model a few times. They train a neural net to substitute it. And then when you move to the multi-scale simulation, you just use the neural network instead, which is very cheap. So the idea is very simple. So just to explain a little bit, so this is the higher scale, and at each element, like we want to deform the material, right? We call this deformation a strain, this epsilon. To deform a material, we need to apply a certain force, right? This force we call stress, this sigma. So what this surrogate model will be doing is mapping this strain to this stress, like how much force I need to deform the material to a certain extent, right? So these are the input and output features of the network. And a lot of people have been doing this for many years. So like mapping these epsilon, these strains to these stresses with neural nets, they are very fast. But of course, I don't need to tell you guys that these networks are terrible at extrapolation, right? So the simplest material behavior that there is called linear elasticity. It means that if I stretch the material, the amount of force that I need to put increases linearly, right? If you get some rubber or whatever, if you get a piece of metal and you try to extend it, the amount of force you're going to have to put there increases linearly with the elongation. So that's what this straight line that you see here. If we train a neural net to give this stress-strain relation up to this level of strain and then keep using it for higher levels, it goes crazy. Because of course, neural nets have no physics, right? People use recurrent neural networks a lot for this because these materials, they do not behave linearly, right? So like just as a quick explanation, so if you load this material, if you follow the black curve here, if you load it, at some point, it will start developing permanent strains. So like the stress like plateaus. And if you then go back, so if you go forward, if you load it and then let go, it will not go back to zero strain. So it will go back to this other branch, right? So it's time dependent as well. So that's why people use recurrent neural nets for this. And if we train a neural net, an RNN for this with this curve, and try to predict the same curve again, it works, of course. But if we first, like, imagine you're testing this thing. If you first just leave it lying somewhere with zero strain for some time, and then you pick it up and test it, the RNN goes crazy, the orange line, because you destroy the memory inside the network.
This distribution shift.
Yeah. And for engineers, this is quite stupid. If you say, okay, I just leave the material unloaded, it should not do anything, and then your model is useless after that. This is terrible, right? So we tried to find a different solution for this problem. And what we came up with is something we call physically recurrent neural network. It's kind of like a recurrent neural net, but what we do is imagine we have this microscopic model, right? That's the model we are trying to surrogate. We're trying to get rid of running this model. Inside this model, we have physical models for these materials, for the fibers and for this resin. They are purely physics. They were invented like 100 years ago, and they are very good. We can trust them. What we do is we get this code for this material and we put it inside the network as it is, like intact. So the network now has a few layers which are normal network layers, and there's one layer in there that's pure physics. So this, you can see this as like a differential programming kind of thing, where we put physical blocks that are untouched by the network, and we let the network kind of use them. So like the task is then of the network is then to tell these material models which inputs to use and get their outputs and combine them into something. And the trick why this works so well is that we use exactly the same models that were in the original microscopic model. We put them there. So if you know reservoir computers, it's kind of like a similar idea as well, right? So we are letting the network use some black boxes. They are not black boxes in this case, but from the perspective of the network, they are.
So for me to fully understand this, you are just using the inner part, the physics. You're just outsourcing the learning part.
That's right.
Yeah.
Yeah.
Okay.
Yeah. So what you see here with this alpha, these are memory variables, but they are physical memory, like state variables that we understand as engineers. So like in this case here, the material loads and unloads with a different, like to a different strain. This would be alpha, like how much permanent strain there is in the material. Okay, and these models know this, and they keep track of their own variables. So this would be like the memory of the recurrent neural network in this case, but it's a latent memory that we understand. It's also interpretable then. Okay, just to make it very clear, this is the code for linear elasticity. We get the strain, we multiply by the slope of a line, so we get the stress. It's linear, right? We get this exact code and we put it in there. And then if I translate this to words, it just says that material behaves like a spring. You pull it and it deforms linearly. This other one is more complicated. So this one, the one with the permanent strains, this is the actual code for that. This code was, well, the theory here was, like I said, invented many decades ago, and it works very well. We put it in there, and it just means that at some point the material starts to develop these permanent strains, and it remembers them. So if you unload, it will know how much permanent strain it has. So none of this code, none of the things inside this code is trainable, so the network cannot touch it. And that's why this works very nice, because if we compare it with an RNN, so like this, what you see here is the training set of our network. We train it by loading it in different directions, right, in this strain space. Only 18 directions, which is not a lot. We compare it with an RNN with 500 whatever directions, and they both work, but if you then test it with some crazy like directions that go back and forth, the recurrent neural net breaks, but our network keeps working. And if you then like level the playing field and you say, okay, let's use these crazy like strain paths for both networks, right? So we train our network and the RNN with the same type of loading. They both work, but if we then go back and test the simple ones again, so these are much more complicated, right, than these. So in principle, these are included in the same distribution as this, so it's not out of distribution. But recurrent neural net breaks again. So it's kind of frustrating to train RNNs for this application. You really need a lot of data. And as a reminder, like the idea of, if I go back a bit, the idea of using a surrogate model is that I don't need to run this guy many times, right? Because if I was okay with running this guy many times, I could just do the multi-scale simulation in the first place. So training RNNs is not nice. This kind of network works very well for us. Here are some learning curves. This is a kind of slide that is very difficult to present to engineers, but to you guys it's very easy. So I just have some learning curves to see how fast the validation error drops. And for our model, we find that like even like 6 strain directions is already enough. And the RNN never reaches that level of error. So it works very nicely. It learns much faster. And like I said, the RNN has this time step size dependency as well. So if you train with a certain delta t, a certain delta time, and you test it with a delta time that's 10 times smaller, nothing should change, but the RNN breaks. So we were very, very happy with this model. For this application, it works very well. One thing already I can mention is you can kind of see this model as like taking some points in this domain. So like this, we have this microscopic domain. Imagine I take some of these points, representative points, and I put them in the network. This is kind of what we're doing. And the points don't really communicate. So at the end of the presentation, I'll present a model where the points do communicate, and that's how we use GNNs. That's what we use GNNs for. All right. So a quick example. So multi-scale simulation, we pull this bar with a certain force and we want to see how it deforms. At some point, we reduce the force, so the bar unloads. And it unloads on a different range because there's these permanent deformations, right? Inside each of these elements, there should be a micromodel, but now there's the network. And it works very well. And to train this network, we don't need to include this part of the unloading. It already knows how to do this because of the models that are in there. So this kind of physical bias that we think is very nice to put it in there. And we also used it to try to reproduce real experiments. So this is a real piece of material in a test frame. We pull it until we break. It is made out of this fiber reinforced material. So if we look at it from the side, you see these fibers, and depending on how you load it, right? So the idea is that if you load this material in this direction, it's very very stiff because the fibers are very stiff. If you load it in this direction, it's very weak. And if we load it with different angles, you see that the load doesn't change, but we turn the material. We get very close to a situation where you're loading it in the direction of these fibers. So that's why if you look at the curves that are appearing here, it gets stronger and stronger, right? It gets stiffer and stiffer. And at some point, it's loaded so close to this fiber direction that the fibers start to realign during the test. It's a bit annoying to explain to you guys, but as you pull it, the fibers are almost at the direction of the loading, and then they start to move, like just by deformation. We wanted to capture this effect, but the best model we had at the time was this guy. And you can see that these two curves are quite off. Like we could not predict the experiment. What we did was to do a multi-scale simulation of the test. But if we did put the actual micromodel in here, it would be too expensive to simulate. So we don't have access to these results. But if we put the network, we get like very nice predictions. So these are the solid lines. So for all of these angles, we get a nice like response that is close to the experiment. So for the first time, we could actually run these models, right? That we couldn't before. So we're very happy with this. Something else we can do, and this I hope you guys can understand, like remember how the network is. So like the features are the strains, outputs are the stresses, but some other features they go straight into the blocks. So like how stiff the material is, for instance. So these are real material models, right? They have a stiffness parameter, they have parameters in there. And they skip this encoder part, they go straight into the blocks. And then we thought, okay, what if we train the network for one value for these parameters and we want to predict a different one? Does it still work? If you don't do anything, if you just use the network as you trained, it doesn't work. So that's what you see in the blue points here. As you move away from the value you trained it, which is here, as you move away, the error increases. That's what you see happening here. The intuitive approach would be to say, okay, I need to train it for different values, right? I need to train the network for different values of these properties. If you do that, you get these like brownish points here. So the error is low for every value, which is nice. But we actually discovered that if you don't train it with different values, if you train it with only one and you just change the value in there, it still works. So these are the green points. So we can transfer to different material properties for free. Like we train with one value and we can extrapolate quite widely for many values. And this has a very clear application in like uncertainty, right? This is what you mentioned also, Elvin. So imagine that we didn't really know what these properties were exactly. We want to propagate this uncertainty. That's the example I show here. Imagine there is a beam and I push it here in the center, it deforms. And I don't exactly know how stiff the material is. So I want to do a Monte Carlo simulation. But for each Monte Carlo sample, I need to run this multi-scale model. So that's quite expensive, right? If we instead just train the network for one value and then just change that value, we can do UQ, uncertainty quantification. That's what you see with these histograms. This is the propagated uncertainty. For this beam, which was, you can see like the finite element mesh here is very coarse, right? There's not a lot of elements. If I went to an engineering firm and showed this mesh for a beam, they would kill me on the spot. Like this, you should not do this. The mesh is terrible for bending. But like we did it to compare the histogram, right? And we see that the one we get with the network is very similar to the one we get with the actual multi-scale simulation. And if we do make the mesh denser, like there are more elements now, so this model could be used in practice. But if we wanted to do multi-scale with this and this Monte Carlo, it would take about 50 years to run. So it's impossible. But we could run it in a few hours with the network and we get nice results. So we are getting access to like modeling results that were just impossible, right? Before. That's very nice. And finally, I get to the GNN. So this is work from Joep. This was the first paper in his PhD. So if I go back a little bit, so before I was doing this multi-scale model, right? So in each of these elements, I had this micro model. And then I showed at the beginning of the presentation that it was very interesting, like for the water ingression application, for instance, to understand what's happening at this scale, right? So to understand how those micro cracks were evolving and so on. If we use a surrogate model for this, be it an RNN or this network that we use, we lose this information, right? We don't have access to the actual microscopic model anymore. We just have access to these average strain to average stress. So we lose a lot of information. So what Joep and I wanted to like agree to do at first was like, okay, can we try to not lose that information? Can we try to come up with a surrogate model that will give us the complete solution field at this scale? And then we thought maybe the GNN is nice for this. So we came up with a GNN model that took into account for each node in the GNN how close it was to one of those fibers, to the 9 closest fibers around it, because we we know that the material response here is very heterogeneous because of these fibers. If this was just a piece of material, solid material, then it would not be heterogeneous. So these distances are the node features of the GNN. So we set up the usual like encoder process decoder scheme for this. We give each of these points a strain, the average strain in the micromodel, and we wanted to compute the strain at every point. So that's what we try to do. And then we want to compute the stress because that's the output. And then we also did it in a hybrid way with machine learning and physics in a similar way as the networks I was just showing, because once the GNN computes the strains, the deformations, we go to this red block here, which is just the physical model again. So this red block are the blue blocks I was showing before. Sorry for the non-consistent colors. So after this point, there is actual physics baked into it. That model computes stresses, and we then average the stresses. So it's like an aggregation operation here, but not done by the network. It's just volume averaging. So we get the stress everywhere, and we average it. The architecture there's nothing fancy. One nice thing that we tried was, if you remember, hopefully these permanent strains, right, that we had, that I called alpha, these state variables, we passed them on to the GNN as well. So the current state value for these state variables is passed back to the GNN. So it's another way to link physics with the machine learning part. And it works. So like we compute these full fields of strains, we compute these full fields of stresses as well, and they are very close to the targets. And if we then take the average of these stresses and we plot it in these curves, it's also quite close to the targets. The nice thing about the GNN is that we could transfer to larger meshes as well. Like we train with very small domains with just a few of these circles, and we can transfer to much larger ones without retraining. So this is what the result you see here. So this is the stress of the GNN, the target stress, they're quite close. This is the error field between them. So this is the difference between them. And it's also quite nice, low errors. And if we average these stresses and plot them as curves, they're also quite close. And something interesting we did as well was to try a few variations of the model to see how much having the physics in there matters, right? Because we're working with these hybrid models. If you look at this model, you can kind of see it as the other network again, but with many points right in there. So you have one point for each point in the mesh. And now the points communicate, which is nice. And then we wanted to see how much like having this physical model in there matters. So we tried a few variations, and we did a few learning curves, which you can see on the left. And we found that if we remove this material model, so this is this one. So like if we ask the GNN to predict the strain and the stress, just like pure data driven, remove the physics completely, the errors are much higher. So if you look at the error in terms of stress is much higher. The error in terms of strain is not that different. So it's these pink crosses here. So the difference is not that big, but it translates into a very big difference in stress, which is the output that we care about. And actually, if you cut these connections and you train without physics, but then online when you do inference, you put physics back, that also doesn't really work. So there's the green points you see here. So having the physical model in there is actually beneficial for training a good model. So I think this is basically what I wanted to show. I think I don't have the next slide. Oh yeah, I have this slide.
Yeah.
So yeah, thanks guys.